Hi guys, this is Investigation 2.1, and in this investigation we are representing exponential functions. So our focus question for this situation is, in what ways are the relationships represented on a chessboard and in ballot cutting similar? So if you remember back to our last investigation, we were cutting ballots apart and we were looking at a situation where we had one piece of paper. If we made one cut, how many ballots would we have? We'd have one cut, we'd have 2 ballots. If we cut it again, we would have 2 cuts, and we would therefore have 4 ballots, and so on. We were able to create an equation that was y equals 2 raised to the x power, where x represented the number of cuts we could make. Then we also have to figure out how they are different. So we're looking for similarities and differences in this situation. So let's get a little bit of vocabulary down. So, words worth knowing. We have a couple of them. First, exponential form. Then we have exponent base, standard form, and expanded form. So, to start out with, I'm actually going to use some of these basic words, exponent and base. Right here we have a 2, and that is in our exponent. You'll always see the exponent raised up above to the right of the number that you are essentially multiplying over and over again. And the exponent will tell you how many times you're going to be multiplying that number over and over. So here is our exponent. And right here, number 5, right there, that is our base. So that's the number we're going to be multiplying over and over. This entire format is called our exponent form. So right here, that 5 squared, or 5 raised to the second power, that is called our exponential form. That is the form that a number can be written. Any number can technically be written as an exponent. If we look at the number 3, we can rewrite that as in exponential form and say it's 3 to the first power. So it's essentially just 3 multiplied by itself just one time. That's it. So it's a very basic format, but at the same time, any number can be written like that. 1 can even be written like that, 1 to the first power, or we could even write 1 as maybe 3 to the 0 power, because 3 multiplied by itself 0 times, it just doesn't exist. All we have left is just 1. That's all it is. So it's kind of fun. Now, if we think about this, we also have standard form, and if we have the standard form of 5 squared, that's essentially something that we see every single day. 5 squared is 25. So right here, this standard form, that is 25. That is our standard form. That's the way we see numbers all the time. Standard form essentially does not show the exponent. The exponent has already been multiplied. We've already done that math, and so we have just 25 left over. So that's our standard form. If we go back to this original equation, or this other equation where we have 3, we can see that the standard form is 3 and the exponential form is 3 to the first power. Last, expanded form. So I'm going to show this with a little squiggly line. Expanded form is essentially taking this 5 squared and writing 5 times 5. So there is our expanded form. Essentially 5 times 5. So in this case, with this 3 and 3 raised to the first power, its expanded form is simply 3. It looks the same as the standard form, which is kind of interesting. So we have 5 times 5, which is our expanded form of 5 squared. So those are some words worth knowing. We have one more word that we need to understand, and that is that of scientific notation. You'll see this often in science class, but at the same time, it's a way that we can write really, really big numbers or very, very small numbers in a way that's easier to compare. Sometimes when numbers get to be too big, it becomes really difficult for us to understand them, and so writing them in scientific notation allows us to be able to look at them a little bit easier and compare them with other numbers, because all we need to do is pay attention to how many tens are behind it potentially for comparing. So scientific notation is essentially the ability to move a decimal point up a bit. So we are literally going to move the decimal point all the way behind our very first number that matters. One thing that's important with scientific notation is paying attention that the decimal point goes behind the first number, because if that's the case, we're putting it behind, or we're making that number between 1 and 10. It's probably bigger than 1, and it's probably smaller than 10. But once it's 10, we haven't actually turned it into scientific notation. We only want one number out in front. So if we were to rewrite this with that decimal place moved, we would start out with this. We have 1 and our new decimal point, 0.995116128. And you're probably saying, well, Ms. Beardsley, what about these last 3 zeros? Well, they're just zeros. They don't really matter. They're just placeholders in this case. And in this case, they're placeholders to tell us that it's more than just ones, tens, and hundreds place. So they don't really matter when we're looking at this smaller bit. They do matter, though, when we go on to this next part. This next part is saying that we know that something that is, let's say, thousands, millions, trillion, or billions, trillions, something that is a trillion cannot be written as just 1. Trillion and 1 are not the same thing. So we need to add a couple of tens to it. And we're not adding them, we're actually multiplying by 10. Every single time we move this decimal point over, we are multiplying by 10. Okay, or we're dividing by 10 technically in this case. So we are moving this decimal point 3, another 3, so 6, another 3, 9, and another 3, 12. So 12 total spaces. So essentially, if I were to take this 1.099511628 and multiplied it by 12 times, I would get this 1 trillion number. And that is scientific notation. I'm able to compare this number, believe it or not, with the 10 to the 12th power to other trillions, or maybe 100 trillions, or tens of trillions, or maybe billions, and compare those and say which number is greater, because I can focus more on this exponent and say if I saw something that was maybe 3.23 times 10 to the 13th power, I could say this is bigger. And I know that simply because my exponent value is greater than this exponent value. So that's kind of fun. It allows us to do that. It helps a lot with science when you're looking at things that are like microscopic, when you're looking at little tiny organisms and trying to figure out their maybe volume in something, or maybe how many microorganisms are in things. We can also look at it with distances, like distances to the sun or the moon, and comparing those. So that's kind of cool. We are moving on. This investigation is all about understanding how things can massively get out of hand really quickly. So in this investigation, we were given this situation where this peasant needed to be rewarded for something that they did for a king. And the peasant said, well, here's a checkerboard. It has 64 spaces, and if you were to put one coin on one space and then double that for the next one and double it again and fill up our chessboard, how about you just give me that money? And what the king slowly discovers is by the very last space, he's paid out more than what is in the kingdom's treasury, because exponents grow quickly. So here we go. We have a checkerboard here. So we're going to play around with that whole concept. We have a 3x3 checkerboard, which is actually not a real checkerboard. It's more like a tic-tac-toe board. But we're going to put checkers on it. So if we have this first space and we put one checker in it, that's awesome. Nothing too crazy. If we were to put on the next space 2 checkers, cool. The third space, we're going to be putting 4 checkers. So we can see that there's a times 2 pattern here. In the fourth space, we're going to be putting 8 checkers. As you can see, hopefully you're shouting out, we're going to put 16 checkers in the next space, 32 checkers, and so on. So this is quickly getting out of hand. And while it doesn't seem like a lot right now, and we're only talking about checkers, a stack of 32 checkers is probably close to 1.5 feet tall, whereas a stack of 1 checker is less than 1 centimeter, so it's like 1/4 of an inch tall. So that's kind of interesting. We're really getting out of hand pretty quickly. So let's fill out this table a little bit. 1 square, we had 1 checker. 2 squares, we had 2 checkers. 3 squares, we had 4 checkers. 4 squares, we had 8 checkers. So I'm seeing that same growth pattern that we saw with the ballast. There's our similarity of a doubling. We're seeing that times 2. So what we can call this right here is a growth factor. We'll talk about this more in investigations in investigation 5. So we have a growth factor of 2. That means our exponent is somehow going to be increasing by 2. It's going to be doubling every single time. Now, what's different, though, is our equation that we're creating. In our past situation, for our first place, we had 1 cut, we'd instantly have 2 ballots. So our starting value is a little different. In this situation, we have our first square, we have just 1 checker, not 2, 1. So with the ballot situation, we had 2 to the first power, and we knew that was 2. So that showed our initial cut would give us 2 ballots. But in this case, we have our initial square. If we were to put a 1 in here, we need that to equal 1. It cannot equal 2 because we're just putting 1 checker in that spot. How can we make that work? Well, check this out. Let's look a little bit further. If we looked at 2 squares, we need that 2 to become 2. So essentially, let's say we look at 2 squares. So we need 2 to equal 2. We need 2 to the second power to somehow equal 2. Well, the only way that can happen is if we had 2 to the first power. So how can we make this exponent become 2? Well, we could subtract 1 from it. So essentially what I'm seeing is 2 to the second power minus 1 could equal 2, because 2 minus 1 is 1. 2 to the first power equals 2. Let's see if that concept works for more situations. If we had 2 to the third power, we need 2 to the third power to equal 4. But 2 to the third power doesn't equal 4. 2 to the third power equals 8. How can we get 2 to the third power to equal 4? Well, if we subtract 1 from it, we then have really 2 to the second power, and that can equal 4. So it looks like our equation for this situation is 2 to the x representing a square, minus 1 equals the number of checkers. Let's see if that works for our initial value. If we have 2 to the first power minus 1, that equals 2 to the 0 power. If you put that into a calculator, 2 to the 0 power, we will get 1 checker. That is exactly what we want. So I'm going to rewrite our equation so we can see it really big. 2 to the x minus 1 is equal to our checkers. That is our equation. So now we're going to use this equation to figure out how many checkers are going to be stacked in the 9th square. 2 to the x minus 1 is equal to the number of checkers. And we want to figure out the 9th square, so that is our x value. So we can say 2 to the 9 minus 1 will equal 2 to the 8th power. And 2 to the 8th power is equal to 256. So I'm going to zoom out a little bit so we can see our checkerboard and that sort of, and see everything else. So we started out just 9 squares ago. We have 256 in this square. We started out 9 squares before with just 1 checker. And then suddenly that checker after 9 squares has become 256. Let's think about those checkers as dollars. If we had $1 in that first square, we'd have $1 in that first square, $2 in the second square, $4 in the third square. That's not a lot. The first 3 squares we're just making $7. But then we have $8, $16, $32. Those next squares we have 48, 56 bucks. That's kind of sweet. The next ones we have 64, 128, and then 256. So just in these last 3 squares, we suddenly have $448. That's a lot of money, and that's just in 3 squares. So honestly, we like with all of this, we're making close to $600 or more than $600 just in 9 squares of a checkerboard. Exponents can really grow quickly, so playing around with this whole concept will help us develop a good, strong sense of how things can grow exponentially. So there is our difference. Our difference initially with this whole idea is this concept. Our exponents have changed. Hopefully this video has helped you develop the whole idea of how to create an equation when we have a different starting point than like our growth factor that we have had in the past. And from there, hopefully you have a good understanding of how exponents can grow very quickly. Enjoy the rest of this investigation. Work yourself through the homework, and and be sure to come to class asking questions if you are not understanding. Thank you so much, and I'll talk to you later.